Dear all, I am Dr. V. Malathi, Associate Professor, EC Department, HR University, Warangal. In this lecture, I am going to explain you about pulse oximeter calibration and testing. And this is the experiment we are going to do in the Google Colab using Python code. I have already pasted Python code and got the results. Let me explain what is this. So now first one import numpy as MP. This experiment simulates the red and infrared PPG signals and it adds noise, filters the signals, calculates AC and DC components, computes ratio of ratios R and then estimates SPO2 using calibration equation. So finally we are going to simulate pulse oximeter system. Process red and infrared IR PPG signals and then estimate SPO2, that is oxygen saturation. What is the expected output? SPO2 valuation around 95 to 100%. It is standardized value internationally accepted and then 2 PPG waveform plot, that is red and IR. And then we will get the simulated PPG signals. A PPG signal has DC component, that is constant part due to tissues, bones and pulsatile blood. And an AC component, pulsatile part due to heartbeat. The red signal, that is red underscore DC, it is equal to 1. The AC, it is equal to 0.02 into NP dot sine 2 pi 1.2 t. That is heart rate, it is almost equal to 72 beats per minute because it is 2.4 into 60. Next one, red underscore signal is equal to red underscore DC plus AC, both components coming under red underscore signal. So first one we will take import NP. Okay, that we will know. NumPy library is Python library is important. Then import matplotlib dot pyplot as plt. So this pyplot module from this matplotlib library functions are imported to give the graphs like bar chart or histograms or simple graph. And then from scipy dot signal. So signal module, it is from this we are importing scipy library. Import butter comma filter. The signal functions are butter comma filter. Now sampling parameter. Fs is equal to 100. That Fs is equal to sampling frequency. It is 100. It is assumed to be 100. That means 100 samples are taken per unit of time or per second. Then T equal to NP dot linspace 0, 10, Fs into 10. What is the meaning? So this time axis starts from 0, ends with 10. And this 0 to 10, in between, how many parts are taken? How many partitions are taken? That is 10 into 1000. 100 into 10. That is 1000. So 10 by 1000. It is 1 by 100. So 0.001. So the time axis will start from 0.001. 1, then 0.02 like that up to 10. Then simulated PPG signal. So we know already it is containing DC component as well as AC component. So first one, red DC is equal to, then red signal RED underscore DC is equal to 1.0. It is baseline, and then 1.2 hertz. It is 1.2 hertz. RED AC is equal to AC signal. So it is magnitude 0.02 and sine omega t. It is converted into frequency. So 2 pi f t. F is equal to 1.2 and then 1.2 hertz into 60 seconds. So it is for unit time 1 second. So 1.2 into 60 means 72. 1.2 into 60. So it is for 1 minute. 1.2 second. 1.2 minute means into 60. So 72 beats per minute. So heart rate is equal to 72 beats per minute. Then 0.02. It is measuring that small amplitude. And then we know that already it is AC, pulsating part. And then final red signal is equal to red DC plus red AC. And then coming to infrared signal, IR underscore DC is equal to 1.2. And then IR underscore AC is equal to 0.03 multiplied by, so the amplitude is 0.03 multiplied by sine 2 pi 1.2 hertz we are taking. So IR signal is equal to DC part as well as AC part. Similar to red signal, but say slightly higher than DC, slightly higher AC amplitude. This difference helps calculate oxygen saturation. And then adding noise. So adding noise. Noise red is equal to 0.005 into NP random dot RANDN LENT, and then noise underscore IR. So noise is added to IR component as well as red component. That is why two part of noise components are taken here. Amplitude is same only 0.005. In the same way here, random noise. So why Gaussian noise from the random noise type is considered here. And then RANDN length T. So what is the meaning? The length of the noise in horizontal axis, that is in time duration, will be taken as same as usual what we are taking for the input signal. So because when we are applying the sampling process, the same thing, if we take 1000 samples per second for input signal, the same 1000 samples per second will be taken for the noise also. That is why the length in time should be uniform. And then what is the meaning? This NP dot random RANDN brace, it generates random noise. So 0.005 is amplitude. This simulates motion artifacts because we are adding the noise. So automatically it will generate some motion artifacts, and then sensor noise. So it will come from the sensor noise also. We are using the sensor to measure. And then ambient light interference. So from the environment also. Then noise is added Because environment from the sunlight we can expect some radiation, red or infrared. Red underscore signal underscore noisy is equal to red signal plus noise underscore red. So signal together with the noise will be taken as input. That is why plus noise we are adding. In the same way, IR underscore signal noisy is equal to IR signal plus noise underscore IR. Now signals look more realistic. The next one, band pass filter 0.5 to 3 Hz for heart rate. So what is the meaning? Define band pass filter. Signal, comma, low cut, comma, high cut, comma, FS, order equal to 4. This function filters heart rate frequencies only. And inside this function, NYQ 0.5 into Fs. So Nyquist frequency is equal to half of the sampling frequency Fs. So here it is 100. Already we have assumed Fs is equal to 100. So 100 by 2 it is equal to 50 Hz. Then low equal to locate by Nyquist. And then high equal to high cut divided by null. So here Butterworth filter we adopt. In that Butterworth filter, the type of filter we opt is band pass filter. So band pass filter means it will have two cutoff frequencies, lower cutoff frequencies and upper cutoff frequencies. So lower cutoff frequency means the below that frequency the components of frequency is lesser than the lower cutoff frequency will be removed, will not be allowed. The frequency components above the higher cutoff frequency will be assumed as noise. That is why they will not be allowed. So, the frequencies between, that means higher than the lower cutoff frequency, lesser than the higher cutoff frequency will be termed as pass band. They are smoothly allowed into the band pass filter. So here, Nyquist is equal to half of the Fs, half of the sampling frequency, 50 Hz, and it is the normalized frequency. So low cut equal to low is equal to low cut by Nyquist. So lower cutoff frequency 0.5 divided by this value. So it is the normalized value. In the same way, high equal to high cut divided by Nyquist. Higher cutoff frequency is equal to 40. 3 Hz. Then the function is to generate the filter coefficients. So for the filter coefficients, B comma A. So numerator of the filter coefficient, denominator of the filter coefficient A. It is equal to Butterworth type order comma. So order normally we are choosing 4 because higher order means there is a sudden transition between pass band and stop band. The distance between the two will be of very low in length. That means immediate transition. So, if the order is more, then steep filtering, the filtering will be smooth. So, the operation will be good. That is why we are opting for order 4. That is almost equal to higher order filter. So 1 means no. So 2, 3 already it is higher order. So beyond 3, 4 means it is very good filter, very high order filter. So now order comma low comma high. So low value already determined, high value already determined, comma Butterworth type of filter is equal to band pass filter already adopted here, and then return filter B comma A comma signal. So numerator comma denominator comma signal. It designs the fourth order Butterworth band pass filter. So this filter function, it is applied to the filter. What we will get? Zero phase distortion. It is cleaning the output. And then why we are choosing 0.5 to 3 Hz? Is there any standardized value, we may ask? Why not other frequency range? So the reason is normal heart rate. It is equal to 0.5 Hertz. It is equal to 30 beats per minute. And 3 Hertz means 3 into 3 Hertz means it is equal to 180 beats per minute. So normal human heart rate is 30 beats per minute to 180 beats per minute. Because 3 into 60, 3 hertz per second. So per minute means 3 into 60, 180. Same as 0.5 into 60 means 30 beats per minute. So only heart related frequencies are passed. That is why these frequencies are assumed as lower cutoff frequency and higher cutoff frequency. And then AC or DC component. AC component. So here, red underscore AC underscore value is equal to NP dot standard over open bracket red underscore filtered. Then IR underscore AC underscore value is equal to NP dot standard IR underscore filtered. What is the meaning? Standard deviation. Standard deviation is equal to pulsatile amplitude. It represents AC part. And in case of DC, red underscore DC underscore value, it is equal to NP dot mean red underscore signal underscore noisy. IR underscore DC underscore value equal to NP dot mean IR underscore signal underscore noisy. So because here DC value will not vary from up and down. It is mean value only, straight line value. That is why mean we are taking into account. We are considering here. Mean value is equal to baseline value. It is almost equal to 0 only. It represents a DC part. And then ratios are. So here R equal to red underscore AC underscore value divided by red underscore DC underscore value. So total red AC to DC value whole divided by IR AC to DC value. IR AC value divided by IR DC value. So AC by DC red divided by AC by DC IR. This is the ratio of ratios R. Here, why this line comes here? This is the core formula for pulse oximetry. So this is the core formula. R equal to AC to DC read by AC to DC IR. Why this formula is used? What is the meaning taken from this formula? Oxygenated hemoglobin absorbs more IR. Deoxygenated hemoglobin absorbs more red. So that is why deoxygenated hemoglobin means it is dilute in red. It absorbs the red for the requirement. So ratio gives oxygen saturation information. And then SpO2 calibration equation. The empirical calibration formula SpO2 equal to 110 minus 25 into R. This is the standardized formula. This is an empirical calibration formula. Commercial pulse oximeters use experimentally derived calibration curves. Then what is the typical output? Around 95 to 100 percentage. The display results then red AC is equal to red AC value. So it displays AC values, DC values, ratio on estimated SpO2. Then plot, so that is what here written, AC value, DC value. For IR AC value, DC value. Then ratio. Then finally it is estimated oxygen saturation, that is SpO2 in terms of percentage. So after finding out these, final oxygen saturation we will get. Then plot the results. So PLT dot figure. So figure size is 12, width, height is 6. Then PLT dot subplot 2, 1, 1. So two rows. Two rows, one column. This is the first position. This is the first position. The top plot is red signal. Bottom plot is IR signal. Next one. 2, 1, first plot, it is red signal. So this graph is drawn time versus red signal noisy, and this is representing the amplitude only. That is why in Y label it is amplitude. X-axis it is time in second. So the title of the first plot is red PPG signal noisy. And then in the second PLT dot subplot 2, 1, 2, second position, PLT dot plot time, IR. So in the same way, whatever we did for red, the same thing is done for IR also. IR underscore signal underscore noisy. It is in Y-axis. So it is mentioned in terms of amplitude. That is why Y label is amplitude. And then plot X-axis is time in second. So the title to this figure is infrared PPG signal noisy. PLT dot height dot layout. So what it means, it adjusts the spacing between the graphs. Then PLT dot show, it is displaying the graph. So finally, what will be the process overall flow is PPG signal, then we are adding the noise, then bandpass filter, then we are extracting AC and DC value, and then we are computing R to R, that is ratio to ratio, and then we are calculating SpO2. Then conceptual understanding, this pulse oximeter works based on red light. It is actually 660 nanometer. And then wavelength. That is, and next one infrared light is 940 nanometer in wavelength. So different absorption for oxyhemoglobin, that is HbO2, and deoxyhemoglobin is Hb. So ratio method eliminates tissue thickness effect. LED intensity variation. So in this way we are, so after finding out the values at a simulating, what we will get, delta S is equal to 0.01429. So 0.01 normal value. So it is for all. So whenever you calculate it, this should be the value. If it is gets exceeding or limited to the value, then it will show the abnormal result, abnormal of the human blood. So we should get the same value for normal person, and IRAC is equal to 0.0213, and then IRBC is equal to 1.2. Ratio R value is equal to 0.8. Estimated SpO2, that is oxygen saturation in percentage, is equal to 89.9, so almost 90%. So here red PPG signal, noisy signal, is similar to this. So spikes without filtering, these spikes will appear in the graph. And in the infrared PPG noisy signal, so amplitude versus time, it will be looking like this. So what we understand in this, from this experiment, we simulate red and infrared PPG signal. We are adding noise and filtering the signals, and then we are calculating AC and DC component. But AC and DC component for both IR and red signals. And then from these values we calculate a ratio of ratios. So from ratio of ratios we are calculating oxygen saturation level using the equation, calibration equation, which is internationally accepted, from this SpO2. So SpO2 is nothing but the oxygen saturation. So what we get? So in the output we are getting 90%. Actually, the expected value will be varying from 95 to 100, but it is very 100% perfect. That is why here we are getting 89, and that is 90% only. So two PPG waveforms plus red and IR were seen in the output. So the PPG signal has a DC component, that is constant value over the horizontal values. It is appearing due to the tissues, bones and non-pulsatile blood. And then AC component, it is pulsating part. It is a AC waveform. That is why it is appearing due to the heartbeat only, going up and down, because heart contract and expand. So due to this we will get the AC component. Next one, due to normally this frequency we have taken 1.2 hertz. It is every time it is for second only, but we are mentioning the heart rate in terms of beats per minute. That is why to convert it into minute we have to multiply by 60. So frequency 1.2 hertz if we take, we will get 72 beats per minute. So, but amplitude is 0.02, very small in amplitude, even though it is of AC or pulsating component. For DC also. So final red value or DC IR value, we will add the DC component as well as AC component, because both are appearing for infrared and red signal. So we have to, but for a red signal, the DC component will be less. In the same way, AC component will be less. That is the only difference we are considering here. Thank you.